teacher, and I've been teaching this course for a little over 20 years now, but it's changed in various ways. In fact, it changed significantly back in 97 or 98, because Professor Masabuchi, who was in ocean engineering, actually, that was when we had ocean engineering at MIT. I don't know if you guys have heard that story yet, but MIT had ocean engineering for 125 years, and then about a year and a half, 2 years ago, merged it with mechanical engineering. So you're now mechanical engineers with the, what's your division? What do they call your division now? Within naval construction. Okay, well, that actually sort of fits, because mechanical engineering used to have their own nickname of SSS, which was soups, suds, solids, and now I guess you got ships. Huh? Okay. Soups being fluids, solids being solid mechanics, and no, soup systems. Okay, soup systems. Anyway, solids and ships, I guess. Okay. In any case, there is the Navy, back when the Navy had a whole bunch of programs for you guys at different universities. Actually had a curriculum that you were supposed to take. I guess they still have a curriculum, but I guess we're down to 2 schools, MIT and Monterey, right? But there used to be, I guess, the last one to be brought was Penn State, but that was for the nukes specifically. Anyway, Monterey, you should know, has been trying to kill the MIT program for years, for pure budgetary reasons, right? Because then they get all your tuition out there. But in fact, MIT killed part of it just because there's not a whole lot of ship construction in the United States anymore. In fact, even the naval construction, as you know, is going down. But in any case, there was a requirement that you take a welding course, and in fact, the welding course that was required was one that Professor Masabuchi, who was in his 80s now, used to teach. He was a professor of ocean engineering, and in fact, he worked on designing ships and welding ships in World War II. But as one of my colleagues at RPI said, not for us. He was over in Japan. Anyway, so Masabuchi's course was required, and it went through welding materials and a number of different things. So when I started doing welding here and teaching a course, I started teaching it on welding processes. And so what we're going to do today is start out the welding processes stuff, which originally had a course number of 337. And what happened in 1997 or so was Professor Masabuchi and this was called welding and joining processes. And it wasn't required for the 13 A's. I used to get 13 A's, taking it as an elective course, and I would get some LFM students, and I'd get some course study students, material students, and people from different places. But then in '97, when Masabuchi retired, quit teaching his course, Professor Chrysostamides, who was head of the department, and I think it was Captain Brown at the time, the equivalent Professor Keenan now, came to me and said, would I add the things that the Navy had in their curriculum, which was specifically welding metallurgy? And I said, sure. And so I added, this was 25 lectures, and it was a 6-unit course. You guys now understand MIT units, which are like no units in any other school in the world, right? But they actually sort of make sense. And I started offering a 9-unit course, which I don't even remember, fabrication technology, I think is what we called it. And what I did is I added another 12 lectures on welding metallurgy, material selection, non-destructive evaluation, and fracture mechanics. And in any case, then for a while there, I was department head, and I started lecture. Well, back in the early '90s, I started videotaping these. So we have Brian Holman back there, who's one of my graduate students, who's videotaping this, and it will go on the web. And so you can go back for the last 6 or 7 years on the web and find my live lectures, so far as that goes. Last year I did fabrication technology, and I think 2 or 3 years ago I did during the summer for the 13 A's. I did those 12 lectures. And my examples, I focused on naval examples that 2 or 3 years ago. This one, we're actually only going to do about a dozen lectures this summer because as the summer wears on, I'm going to have other things to do. You're going to have to take 2/3 of the course by video. Okay. Some people take the whole course during video, other MIT students. And in fact, the last couple of years of 13As took it during the summer entirely by video because they found this was an easy one to just fill up your time, which you will find they do everything they can to fill up your time. There's not much you have to do in the course. Okay, you're supposed to come to lecture, and the sheet I just handed out has some selected comments about the class that students have made in the past. This professor speaks very fast, and it's unlikely you can follow everything as he goes along. You can read the comments. My favorite comment was, since you're eating breakfast, and I certainly don't mind if you bring breakfast to class, okay, so far as that goes. But my favorite comment was into the term evaluation. They just wanted to know what course I taught around lunchtime. So in any case, you should be signing up for 3371, which is 9 units, and you're going to have to take about 25 of these by watching the videos like other people do. Now, there's a couple ways to do that. And one of the things, I can hand out the schedule, which I put together last week, which is already out of date. This is my travel schedule. And we basically meet every day that I'm in town, which I'm not here tomorrow, for example. We'll be in New Orleans. I should be around the first 3 days of next week. Now it turns out I might be here all 5 days next week, but I won't know until the beginning of next week, so stay tuned so far as that goes. I might be gone on the 27th now. But we're only going to have about 12 lectures. If I actually get all those in, we'll probably be done just after the 4th of July, somewhere in that week of the 5th, 6th, or 7th, with the live lectures. However, that brings up a class decision. Do you want to watch the videos in this room at 8 o'clock in the morning, every morning? Because Brian can bring the videos, and you can start. This module is really separate from this module. Okay, so you can start watching the bottom module there on material selection and things like that, and we can intersperse it with my lectures, which would be the first half of the 25 lectures. Or do you want to take it home and let your spouse watch it with you if you're married, or your roommates if you're not married, whoever you are. I mean, I was once looking at an oil video from down an oil well 2,000 feet deep that had failed and was full of water, and I had the video on. My daughter, who's now married with children, but she was about 5 years old at the time. There was just this round circle with bubbles every now and then coming through the water on the TV screen, and it went for 2 hours. Anyway, I was sitting there watching it, and Rebecca comes and sits next to me as a little 5-year-old, and she watches it with me for 3 or 4 minutes. Finally, she says, "Daddy, what are we watching?" So you can watch it at home. I mean, I've had people tell me they watch it while they fix dinner and things like that. Do you want to do it as a class on the days that I'm not here, in which case you can still have breakfast? Or do you want to do it on these other 25 on your own over the summer? Or you want to figure out later?
I'm okay tomorrow.
Okay.
We'll talk about it.
Well, you can't tell me tomorrow because I won't be here tomorrow. But you can decide tomorrow. If you decide, you got to let Jeremy know, so they'll bring breakfast for you. Okay. You also have to let Brian know, or you don't have to do it tomorrow. You just take tomorrow off, and you can decide next week how you want to do it. I don't care. I mean, you can take all 37 over the summer for the next 37 days, so far as that goes. But that's something you have to decide, and you actually can split it. I've had groups do it where 2 or 3 people just didn't want to come in that much earlier in the morning. But the 13As, I keep calling it 13As because that's what I've been calling for years. Now you're the 2 whats? Two ends. Okay. Yeah.
Are those lectures on the web?
You can get them off the web. You can also get them as a DVD, and I don't know. I don't think we have anything but DVD. We used to have video or DVD, but I think now we just have DVD or webcast, live webcast. Well, not live, but
I can download it and play it in Windows player or some
Yep.
other real player or
Yeah.
whatever. What?
people around the world can do it.
Quick time.
Quick time. Quick time. People around the world do it. They don't get credit for it because they don't pay tuition.
Is there a deadline for the completion of these? I mean, you know, if you wanted to wait till, say, the 18th of July, start locking these? Would you and
If you
then,
could do that,
okay,
I wouldn't necessarily advise that given all your other courses.
Right.
Okay. Now, however, the only thing you have to do for the course, you can either, there's the handouts I gave you, there's actually 2 sets of handouts. I think Jerry only gave me the 337 handouts. There's a 3371. These are old handouts, you don't have to read them, okay? In fact, in there, you may have just hit it, there's a chapter 16, no, that's not one. There's a 3rd or 4th one in there, it says chapter 16. There it is, that was it. Yep, no, this one, chapter 16. Right there, why don't you hold it up so they can see it, or I'll put it up on the screen. Okay, you got it, it's about 5th or 6th or 7th in there. It looks like that. And it's called chapter 16 because back, I don't know, probably more than 10 years ago, a professor over in mechanical engineering was writing a book on manufacturing, and they asked me if I would write a chapter on joining. So I took my notes for 337 home and spent a day just writing chapter 16. So chapter 16, if you want to see an outline of these 25 lectures, it's right there. You can skip everything else. The rest of the stuff is just kind of supplemental material. Some of it's kind of dated, I haven't updated it, but if you're really interested in the topic, there's some papers on there that will follow along with the lectures. There's no specific reading assignment. You have to come to class, listen to me tell stories, and I would much rather tell stories than lecture on what I plan to lecture on, okay? In fact, it's sort of become a game with the students. Can you ask a question, and can I figure out a story to respond to the question? Okay? Do I have an anecdote to go with your question? So it's, if you want to make it a challenge.
Are all 37 lectures on the web?
Yeah.
How do I know
Well,
which 12 you're going to do?
I'm going to do the first 25 of 337. The web is broken up as 337 and 3371, welding processes and fab technology.
Okay.
I'm going to do the first 12 of these, and then you're going to have to pick up somewhere in the middle. But they have titles like adhesive bonding or diffusion bonding, so you'll know kind of where we were, okay, when I stopped, you know, in the first half of July. Fab technology, there are 12 lectures, and actually we have them in there for every year that we videotaped them. And I think it was about 3 years ago, it was actually over in a classroom in Building 5, so you can kind of tell by looking at the video very early on and see if it's the Building 5 classroom. I did it live for the, at that time, 13As, the 2 ends. And I used specific examples from mostly naval applications. I tried to, you know, give my examples, my anecdotes from naval applications. If you don't want just naval applications, when I have the manufacturing students, sometimes I'll emphasize if I have a lot of automobile folks or something, examples from different industries. I don't care which ones you take. You probably ought to take a consistent set because I don't always tell the same story in the same lecture each year. Okay. Someday, I have some former students who are supposed to be collecting some of these things because I tell different stories different years. They're not always the same. Now, the other requirement, I have to grade you individually, and so you have 2 choices, and this is on the web too. The grading is officially A through F. I'll tell you, I've only given 1 grade in this class, actually 2 grades, pass or one of these other A through F grades for the last 20-some years. Okay, because when I first started teaching this, it wasn't required for anyone. It actually is required for you now, since Professor Massaguchi retired. But since it's not required for anybody, I taught this as a course. Let's just come and talk and learn, and not worry about quizzes. Don't worry about assignments. But I do have to do something. So you have your choice of either a 10-page term paper, and I will grade you down if it's more than 10 pages. Okay? I don't want to have to read it, and I don't want you to take the time to write more than 10 pages. Or, and that's on any topic that you're interested in. And if you're going to do that, you need to come make an appointment, sit down with me for 10 or 15 minutes, and I'll help you, guide you a little bit on the project. Or you can do a problem set. The problem set is, if you go to chapter 16 in there, the very back of chapter 16 has a set of 10 problems, and they're open-ended problems. One of them does not have a solution. I made a mistake in putting the numbers in it, and I've never corrected it. But they're open-ended problems because some of them actually do have what I call deterministic answers. You know, it's 70, okay, is the answer. And everybody gets the same number, pretty much. But there are other questions. There is, like problem 2 on the rivets. I don't know what the right answer is. I've gotten so many answers from students over the years that I'm confused at this point as to what the right answer is. So they're not like your undergraduate problems where, you know, on a quiz you could always tell if you didn't use all the pieces of information there was something wrong. Okay, you know, you could back engineer the question. So some of them may have extraneous information, some of them may not have enough information, which basically means you have to estimate or go to the literature and kind of come up with a number. One of the advantages of most of the students end up doing the problem set because you are allowed to do the problem set as in groups. The largest group I ever had was 18 students turned into one problem set. Okay, you have all your names on it, and what I ask is, I don't care if you assign it with 12 or 13 of you, you assign 10 of you get assigned one problem each, as long as you then sit down together and have the person go through and explain how they did it. Okay, so it's not a hard course, folks, and that's it's one of the reasons why they would throw it in as an overload during the summer. There are some students who will wait and just do it by video. I used to live lecture it in the fall, but now I do a thermodynamics course in the fall. So I decided, hey, if you guys are going to be all watching it during the summer, I might as well live lecture it to you. I'd rather have questions than just do it to a small class. Okay? Any questions? So you either have to do a problem set. My bet is you will decide to do the problem set. But some of you may decide you want to do a term paper, and that's fine. And we don't have class tomorrow, but we will on Monday, 8 o'clock. And actually, today, since we started about 10 minutes early, and I have to go catch a plane in Washington, we're probably going to stop at about 20 of. Okay? I will generally start right at 8, and we'll stop at about 10 minutes of rather than 5 of. Because how many of you have to go over to Sloan? 2 of you.
Not today,
Well,
but
yeah.
we usually have Fridays
Okay.
and Tuesdays.
Okay. So, but I understand that, and so in general, I'll start on the hour and finish 10 minutes of the hour, just to let everybody. And you're welcome to go back and finish up the donuts and croissants and stuff. And you'll notice there were Rice Krispie treats I found over the years. People like to stock up for later in the morning. And I don't, you know, the whole thing started because originally I used to teach this from 8 to 9 because I had students from, you know, a bunch of different departments, and the only time where everyone was free with no conflicts in the regular 9 to 5 schedule was 4 o'clock Friday afternoon. That was the only hour. I did a survey once. So I started teaching it from 8 to 9, which is outside what used to be the official MIT. You had to teach your classes between 9 and 5. So I started doing it illegally. And then Sloan moved their classes back to start at 8:30. So I made a deal with the students. Come at 7:30, I'll give you continental breakfast. And so for some years we did an hour and a half, and some years, you know, different things. This year I understand some of you come on a shuttle from Hanscom or something, doesn't get here until 7:45. So we'll start at 8 and we'll finish at 8:50. Okay, I think that's all the procedural things. If anybody has any questions, let me know. So far as when you watch the other videos, you have to turn in your assignment before I have to turn in the grades, obviously, which is sometime mid-August. I don't know when. I don't even pay attention to when the last day of class is because I'm going to finish up with you before then. Okay?
It's your curiosity.
Yeah.
So we won't, Sir, we won't meet tomorrow to watch a video. We'll let you know on.
Okay, that's fine.
Yeah, that we're gonna do that.
Because you'll have plenty of time, I think. And like I say, you can watch it online, at home, or if you want to get together as a group and buy yourself breakfast, you can do that. And Brian, you actually probably wouldn't have to be here. You could probably teach one of them to bring, or there's a DVD player there, and they can probably figure out how to run it if they decide to do it as a group and eat breakfast. Okay, other questions? Yeah.
The sheet you have in the overhead, is that in our packet somewhere? This was looking for.
No, that's on the web.
Oh, it's on the
So
website.
it's www.eager.mit.edu, and it'll have something on there that says my courses, and then there'll be several courses. One's 337, 3371. So if you hit 337 and 3371, it'll have all that stuff. It'll also have most of the overheads and stuff. In fact, if one of you that's got a computer, and there's 3 of you, want to earn some money, about $50 a lecture. If you're going to take notes anyway, if you will take them, transcribe them, and have Brian get them posted on the web to go with these lectures. When you look on the web, you'll see that there's a whole set of notes. I try to make this so you don't have to do anything. They're the students in the years past have posted the overheads. They cleaned up my overheads. I haven't even, some of mine are still handwritten, but they cleaned them up so that the overheads are on the web. There's even a student set of notes that goes with the lecture. So you don't even do print out the notes, and you don't even have to take notes while you're watching the movie. Okay, isn't that great? So did you want to volunteer for that, or did one? There's 3 of you that are eligible, right? Because you brought computers, right?
Yeah, I'm volunteer.
Okay, 2 of you can figure out how you want to split it up, but I'll pay $50 a lecture as a bounty for your notes. Okay, but they got to be in a form that a digital form that we can just stick them in the computer. And if you want to see what people have done in the past, and because every lecture is a little bit different, I like to have a set of notes that go with that year and that set of live lectures. So, okay. Other questions? Let Jeremy know what you like to eat, and he's going to have to figure out how many cups of coffee to fix each morning. And Brian, do you get caffeine in the form of soda? I don't know how many of your caffeine soda addicts. Sprite doesn't have a lot of caffeine, but anyway, I mean it's okay. Not everybody. I don't drink caffeine, but a lot of people need it. And I learned in some classes, they get their caffeine from Coke. Some people get their caffeine from coffee. Anyway. Okay, so why bother to study welding and joining? Well, in your case, it's because the Naval Sea Systems Command said so, right? But there's other reasons. And in fact, we'll probably meet again because I started teaching something during independent activities in January a few years ago, where we have the students, your class will come back with some experience from your prior naval experience, and you'll get 20 minutes to explain something either that you saw and didn't understand, or you saw and solved that you want to present to people, some naval thing, and then I will then sort of again, can I provide a lecture based on your experience? Now, I actually will get a head start because you'll tell me what the topic is ahead of time. But in general, I find that mostly come up to be corrosion problems. And what happened is 3 years ago, I was lecturing the welding course to the Navy students, and I realized that the guy who used to teach corrosion is retired. Now, one of his students over in nuclear engineering sort of teaches it, but I know he teaches nuclear engineering corrosion. And you guys kind of need other things. So, how many were in soup ships? Okay, how many were on ships? I guess all the rest of you. Not all of you raise your hands. Oh, submarines. Okay. Well, how many were on boats? Okay, you haven't raised your hand yet. Where are you?
I was an instructor at New Power School, and I was in the shipyard for the last 3 years.
Okay, so you were a ship. Okay, but not soup ship.
Right.
Okay. It's not. You don't have these soup ships. No, they don't have soup ships. They want to put in as a ship construction. Oh, okay. Okay, they reorganize things all the time. Okay. any case, we'll probably do this in January, where you get to come in and make a 20-minute presentation. We've had a lot of things. We've had people, talk about the environmental concerns on removing paint prior to repainting the hull. We've had people talk about corrosion problems in the bilge or in some tanks. We've had people talk about some welding problems, specific welding problems. We had one where they had a mix-up on a valve. This actually happened in the Gulf on a 3,000 PSI airline. And it turns out it was sort of interesting because the student that was on the ship that actually had the problem made the presentation, and another student in the class, they didn't know it, happened to be back at the Naval Supply Depot or was interacting with the Navy. I guess they were at the shipyard and they were involved in supporting that ship out in the fleet. And they got involved with the supply depot and they found out that, they had the wrong chemistry brass, which was causing stress corrosion cracking. Well, I think it was stress corrosion cracking. No one had ever figured it out, but it was kind of a problem because I guess when your 3,000 PSI air system goes down, this was during the, not the first Gulf War, what do we call the second one? Iraqi Freedom. Okay. Yeah. It was in the middle of that on a destroyer. People were not happy. Okay, so let's talk about why bother to study welding and joining. For me, I could say I think it's exciting, and hopefully I can convince you that there's some excitement to it. But one of the things, it's integrative. And by that, I mean, welding is not a discipline. I'm in the materials department, but you go to some other school and the welding engineer or the person who teaches welding might be in the civil engineering department, they could be mechanical engineering. Quite often, a company will have some big welding problem come along and some manager will take a physicist and say, you're now a welding engineer, okay? Go solve our problems. It involves chemical engineering, thermodynamics. One of the things I like about it, aside from the fact that it was one way to focus to give me my tenure, because everybody says, oh, that's what Eager does, he's a welder, okay? And I've been involved in the Welding Society for years, okay? Not so much anymore, but I was for many years. In fact, when people ask me what I do, I just tell them I'm a welder. It's easier than explaining I'm a professor from MIT, which always raises other questions. If I just say I'm a welder, that usually stops the question. Actually, when they later find out I'm a professor at MIT, that actually starts the questions again. But anyway, it's integrative. You can work on anything you want. And I have worked on all kinds of different things. Because I'm not like your typical MIT professor who studies more and more about less and less until you know everything about nothing. Okay? I actually try to be a little bit broader. And so, when we get to plasmas, I'm going to teach you how fluorescent lights work. Okay? Because it's a plasma up there. Okay? And I'll teach you why it's more energy efficient than an incandescent light. And nowadays, we can even talk about why the semiconductors are even can give you light even more energy in a more energy efficient way. So, just like you can ask me questions, and I'll see if I come up with an anecdotal story. I like to both take welding problems and try to figure out how it might apply to some other problem in the world and how the way things work in the rest of the world. But I also like to take what we know about other things in the world and try to apply them to welding, which is where I do some of my research. Okay, so it's an integrative discipline, and actually, how many of you are mechanical engineers by background? How many of you are electricals? How many of you are agriculturals? Could be. Physicists. Okay. Chemists. Chemical engineers. Who hasn't raised their hand yet? Yeah. What are you?
Dead water protection.
Dead water? Oh, wow. I didn't know they existed anymore. Okay. Yeah.
Ocean engineering.
Okay. From where?
Navy, USA.
Oh, okay. Annapolis. Okay. Okay. Yeah.
I did systems engineering at the CAD.
Okay.
Marines, yeah, I think that.
Okay. to ever get about the academy. Actually, my father went to the Naval Academy. Graduated class of 44 in 1943. Okay. He was ahead of his time with his whole class was too. He got through in 3 years. Anyway, another reason is the importance of welding and joining. Okay. In one way, welding has improved what we make. I mean, can you imagine trying to make the types and sizes of ships we make today by riveting them together, which is the way we did it before, mostly before World War II. I can pass these around. These are some photographs from the, I guess it's N-Star now, but it used to be Boston Gas, you know, the people who supply natural gas to homes in Boston. This is down in their tech center, south of Boston, and this is a gas pipe that was installed in the Boston system underground. It's cast iron, and it's got oakite stuffed in here. But oakite is basically rope with some other mineral gunk, okay, sealant put in there. And so you got this cast ring, and you have these cast iron pipes, and that's how they used to join them in the old days. That's a head-on 6-inch cast iron pipe, and it tells you which street. And it says 1836. Okay, that's how they were pumping gas to light the street lights. Here's another one. I guess it's not quite as, but the sealant's not quite as good on this one. Here's a bell and spigot joint, and actually the one I didn't take a picture of, they actually have a piece of gun drilled timber wood. You know what gun drilling is? It's the way you make gun drills. But if you tried to take, if you had a big long piece of stock and you wanted to drill, and you had a long drill, just because it's not, the drill's not infinitely stiff, it would tend to walk and try to go out the side. So in gun drilling, you actually rotate the stock at the same time you're counter rotating the drill, and that keeps the thing going straight down the center. Okay, because if it starts to walk, and it, you know, it's starting, the drill's starting to walk this way, but the stock is going the opposite way, so you actually have to go in opposite directions. Not everybody can do that. You can try that yourself. I perfected that in high school. Anyway, so they gun drilled wood, and that's how they first started putting gas through underground streets of Boston. Just big logs that they would gun drill. It might be a 12-inch long with a log with a 2-inch hole, and it might be 10 feet long or 20 feet long. Maybe not 20, but 10 to 15 feet long. And then they would just seal them up. And of course, they'd have a few leaks, but you know, they didn't have that many fires, hopefully no explosions. But we have better ways of doing things now. I actually didn't bring the plastic pipe, but I will be bringing the piece of gas piping that we use today, which is plastic pipe. And of course, somewhere in between there, we started using steel. And in fact, a very big deal, the first critical all-welded structure out of by arc welding was the big inch pipeline in the early 1930s. They were bringing the first gas up to New Jersey from Louisiana and Texas. It was a 30-inch gas pipeline, and it was welded. Now, people had welded things before, but they never welded things that were really critical. Okay, and then so they were successful with that, and they didn't blow up too many cows in the fields. And fortunately, those big pipelines, we actually have about half a dozen major explosions in the country each year from big gas pipelines of 1,000 psi gas. But you don't really hear about them very often because they usually do occur. They might kill a few cows or burn up a cornfield, and then the oil company goes, or the gas company goes in there and pays off the farmer, and they, you know, might be in the local paper, but it doesn't hit the big news. It did happen a few years ago down in Edison, New Jersey, which everybody knows New Jersey. Edison's, you know, a fairly built-up area, and it was a 42-inch pipe, and the flame shot 600 feet in the air in the middle of the night, and just the radiant heat melted the rooftops of the apartment complex across the street. No one got hurt other than a woman about 3 miles away supposedly had a heart attack and died. She may have done that anyway without the fire, but you know, it's sort of like the time they had a release in Charleston, West Virginia, at a chemical plant, and there's an attorney down there who files class action suits whenever the chemical plants have a release, and so and I read this complaint. One guy who lived 5 miles downstream, you got to remember the plume kind of goes up in the air at about 30 degrees, right, from the horizontal. So 5 miles downstream, that plume is, you know, 2 miles in the air, right? This guy's 17-year-old dog died 9 months later, and he was attributing it to the release of the chemical. Okay, I thought 17-year-old dogs are doing pretty well the last six months after the event. Anyway. So people will claim all kinds of things as far as that goes, but it has improved what we make starting in World War II because of the importance of trying to build ships. We started making all welded ships, and most of you probably know what happened. What happened? We built Liberty ships. You know how many? 4,694 Liberty ships. We also built some T2 tankers, and so anyway, I think there was about 6,000 total of all of these. 970 of the 4,700 suffered casualties involving fractures. 24 vessels sustained complete fracture of the strength deck. 1 vessel sustained a complete fracture at the bottom. 8 vessels were lost. Of these, 4 broke in 2 and 4 were abandoned after fracture occurred. 26 lives were lost due to structural failures to welded steel. And this is the famous picture of the Schenectady sitting there at harbor. You guys haven't seen this picture before? Okay, it's in a lot of fracture mechanics books. However, it also happened out at sea. Okay, not a good day. Okay, that didn't happen in riveted ships. Anybody know why? In a riveted ship, if you start a brittle fracture, it runs to the end of the plate, which is where the rivets are. And it stops. There's no way to carry that fracture into the next plate because you have a seam there. Okay? In an all welded ship, it goes right through, and it goes, as you can see, all the way around. And so that's why they're friction stir welding the new well, it's a private jet that's going to compete with the Learjet. And they're friction stir welding the aluminum. I guess I'll bring one of those things in too. But that'll be, right now, aircraft are riveted. And so if you get a fracture, the fracture could run all the way across the panel, but it stops when you hit the end of the sheet. Now, with an all welded aircraft, you could have one of those split up. It'll even be a worse day than losing your ship in the middle of the North Atlantic, okay, if that happens. But so there are problems that come along with welding, but it has improved what we can make. It's increased the size of what we can make. It's reduced the cost. Significantly reduced the cost of things compared to riveting and stuff. Okay, welding has improved the reliability of life, in spite of all the things people say about welding and the fact that most welders end up becoming forensic engineers who are studying failures. Okay, and I almost brought in a book called Colossal Failure or Engineering Catastrophes, which is in its like 2nd or 3rd edition, written by a welding engineer from South Africa, talking about different types of failures. I remember the first year I was a faculty member at MIT, the professor who's now retired, who taught fatigue and fracture, was telling his class, and students came to me and said, "Do you know that Professor Plough was saying that something won't fail unless it's been welded?" And I thought, well, first I thought, what's he maligning my field? And I thought, oh no, that's good. I'll have a job for a while. As long as welds keep failing. But there's a reason why they fail. And actually the second part of that story is I learned to appreciate that. Something won't fail unless it's been welded, and I tell my class that. So in 1992 in Montreal, I was giving a lecture at the beginning of the International Institute of Welding, and this was kind of an open, plenary session. It was the Boudreauxmont lecture. I had 500 of the world's top welding engineers out there, and I was giving this talk on welding, and it was sort of like this first lecture, today's lecture, a little bit different. But I put up this slide that says, something won't fail unless it's been welded. and I attributed it to Reggie Blue. And the room was just dead silent for a couple of seconds. And then slowly laughter rippled through the room, okay? But at first, those welding engineers didn't know exactly what to say, okay, about that. But things do fail, but there's a reason for it. Anybody know what the reasons are? Why welded structures tend to fail? Or when things fail, they fail more often at welded joints?
Because it puts a flaw into the material where there might not have been one before.
It can. Welds are often not as strong or defect-free as the rest of the material. I mean, you cast a piece of steel and it's full of porosity. But after you roll it, you've healed all that porosity, and now it's wrought material and it's gotten rid of all of those defects. Well, a weld is nothing but a small casting, and it'll have some flaws in it. And many times, it may not match the strength. Particularly in aluminum alloy, it's very hard to match the strength of the weld metal to the base material. So the weld may be inherently weaker, okay? Not always, but it can be. You were going to say something?
Well, I was say that the welding process needs a product that's not really homogeneous, and there's imperfections or whatever, whereas your rooted example is the materials are all good quality materials, and the joint will be.
Except the rivet's got a natural hole, and it's always going to be a few cracks starting in the rivet. But no, your point is correct. The real problem, though, is really that we put welds in the most highly stressed locations. We put them at the corners. That's the stress concentration. Your point is they're not homogeneous, and that creates what I call a metallurgical notch. Okay, slight difference in modulus or slight difference in strength, and that creates a stress concentration. I mean, if I don't match the strength perfectly, the weld is either stronger or weaker. If it's weaker, it turns out I'm concentrating all the strain energies are going to go in that one small little volume, and the weld's going to fail. And every 10 to 15 years, the Navy starts looking at, can we use undermatched filler metal, okay, on steels? And the answer is no. And the reason is, they have done it in certain locations, but not critical locations. You generally want a weld metal that's stronger than the base material, because when you start straining the whole structure, you don't want the small volume to yield, you want the big volume to yield, okay? You can absorb more strain, more stretch, if the bigger volume is stretching rather than concentrating all that strain in the small volume, okay? And that gets into toughness issues too. You can absorb more energy if you're absorbing it, if the softer material is the larger volume of the material. But even more important than that, we tend to put the welds in the most highly stressed locations, at the corners, at the edges, okay? Just because that's the natural place to put them. Now, if you go to an aluminum design manual, they'll tell you to start using nodes and putting the welds outside of the corners. You might cast a node. You look at the Audi space frame automobile that Alcoa helped them develop. They basically will have a node for that space frame structure, and you have all these tubes coming out of this cast node, and then they weld a couple of inches away from the intersection. Okay, so you have a homogeneous material at the corners where you're going to get all your stress concentrations, and you put the weld at the lower stress location.
They do that on bike frames.
They do that on bike frames, okay? Because you can afford to do it on a $60,000 car. Anybody who's going to pay $10,000 for a bicycle deserves to get whatever they get. Actually, I understand bikes can cost $20,000-$25,000 now.
There's a titanium welding shop in my hometown. They started out $10,000 a frame.
Yeah. Well, I remember a few years ago, a $3,000 bike was a big deal. But I just read about $20,000 bike. There's a titanium welding shop here in Cambridge. There's always, every year, there's some students who want to, in fact, there's some group that's coming this summer for some vehicle, thing. It's a group of undergraduates from around the world, and of course they want to make graphite fiber bikes and things, But we'll talk about that. In fact, we'll talk about it in just a second here. Okay, so it's important because increased size, reduced cost, improved reliability in life in general. But it's also ubiquitous. What does that mean? Ubiquitous means something's everywhere. Okay. The example I like to give is, think of the largest standalone manufactured product that you can think of. I mean, I'm talking about a manufactured product that actually has utility in its own right. Okay, so the largest piece of steel that we manufacture in the world, a single piece, is a 700-ton generator rotor forging for the 1,000-megawatt generators of the biggest utility plants. And then by the time they machine it down, it only weighs about 300 tons. Okay, but it starts out as a 700-ton casting. That's just a big paperweight. It's not very useful by itself as the original casting that's going to be forged and everything in the machine. Now it's pretty big, but it's not really standalone. Okay, so okay? Here's your first quiz question. I'm not going to be graded on this, but what's the largest standalone manufactured object that can be used in its own right?
Manufactured with welding, possibly? I mean,
No, I'm sorry, that doesn't contain a joint. Okay, I'm sorry, that doesn't contain a joint. I'm sorry, I forgot to tell you that. I only got 2.5 hours sleep last night. I had to go. I was down at looking at a utility in Rhode Island until 2 a.m. Now, people originally used to say, well, a nail or a needle, you know, it's just a piece of steel. Someone then came up with a cast iron frying pan. But you have to say cast iron because if it's aluminum, it's going to have a plastic handle usually. And there's got to be a joint there between. So one of the things you learn is when you start thinking about this problem, it has to be a monolithic object. It has to be made out of a monolithic material. Okay? People said, oh, a Coke bottle. Or not a Coke bottle, but I agree you can say Coke bottle if someone said a milk bottle once. I said, no, you got to have a cap on it, you know. You got to have join the cap. It may not be a weld, but there's a joint there. How do you seal that? So I said this once when Professor McClintock, who's got to be, was almost in the mid-80s now. I said this one time at a conference, and Professor McClintock worried about this for the next month. And he came back to me and said, an anvil. Okay? So, okay, you can think of a big anvil. In fact, the biggest anvil I've ever heard of was about the size of this room and weighed about 100 tons. So there are large objects, but it's hard to think of things that don't contain joints. And then it turns out that the quality of those products is directly related to the quality of the welds. And we'll finish up here today. Welding is a large fraction of the manufactured cost. Okay, and by that, if I handed this out to you, but it should be on the web. Anyway, the cost of the material is a relatively small fraction of the cost of the final manufactured product. I estimate for a pipeline, the cost of the pipe buried in the ground is about 30% of the cost of putting in an oil pipeline or a big gas pipeline. For an automobile or an aircraft, it turns out the cost of materials, the raw materials, is only about 10% of the final fabricated cost. For a semiconductor or a spacecraft, it's only about 1 or 2%. And we can talk about that later. One of the examples, a few years ago, I was sitting on a committee for NAVC to look at using HSLA 65 in aircraft carriers. Turns out an aircraft carrier gains about 250 tons a year. So you've got a roughly 90,000 ton ship. But if you look over the history of the Nimitz hull, you'll find that they gain about 250 tons a year. Unfortunately, it's mostly top heavy, up the top rather than the bottom. And so they figured they could get 2,000 tons out of the ship. Our Newport News did a study and said they'd get 2,000 tons if they could go from 50 KSI steel to 65 KSI steel. And I remember the cost of that steel was going to be about $2,000 a ton. And my little rule, I said, oh gee, that means it's going to cost $10 a pound as fabricated in the ship. And it turns out I later learned that Newport News had done this $500,000 study for NAVC, and guess what? They estimated it would cost them $10 a pound fabricated. Okay. Now, if they just give me the $500,000, I'd be sold. Okay. But it actually works pretty well. And in fact, I have a little note here that I did a couple of years ago. I guess probably at the time of the World Trade Center. The World Trade Center had 250,000 tons of steel. So you got 250,000 tons of steel, and that's at $500 a ton, and that works out to $125 million if I got this right. Okay. The cost of the World Trade Center buildings was 176 billion? No, 1.76 billion. Okay, just under $2 billion. And you say, well, that's not 10%. Well, they had some concrete and some other things in there. And maybe the World Trade Center was 15% of the cost, okay, of the building. But the point is, you look at the raw material costs, they're not a very large fraction of the overall cost. And this next one, actually I have it over there. I found this morning.
When you say raw material, you're talking about the ore, not.
No, I'm talking about the steel beams.
Actually buying them as beams?
Not fabricated, but just buying the beams from the steel mill.
Yes,
Okay.
already processed.
Or buying, if you're talking about an automobile, buying sheet from the rolling, sheet that you're going to stamp and do everything to. So it's not raw materials as in terms of ore, but it's in terms of the stock, what you would go to Home Depot and buy if you're going to build something. Okay. Now, obviously, you don't go to Home Depot, but maybe somewhere in there. Here it is. So I estimated once that materials will cost you 10 to 20% of your fabricated structure. You're going to spend 10 to 20% on welding and joining. Other fabrication costs, which can be forming, machining, painting, whatever you want to call it. I just threw in there NDE on a critical structure, pressure vessel, naval ship, something that is more critical than just your average Ford Taurus. It's going to be 10 to 20%. G&A is going to, depending on a critical structure, is going to be a little high. It's going to be high because you have a lot more engineering, and your profit is somewhere between plus or minus 10%. Okay, if you run through those numbers. So materials cost is a relatively small fraction. Welding and joining is roughly the same as NDE and the materials cost, but the problem with welding is welding comes at the end of the manufacturing process where you've already invested all these other things in it. Okay, you paid for the machine, you paid for the material, and so if you end up with scrap, you tend to lose a lot more value than just the value of having done the welding. So that's enough for today. Thanks. We ran over a little bit. Okay. And in fact, if you all are